Hello and welcome to our very first Warwick Data Science Society Mini Talk. I'm Yasser Qureshi and I'll be your host for today. We've all heard of blockchain, but do we really understand how it works? Today, our speaker, Raul-Octavian Rus, will explain what blockchain is and how it works by making one. Raul is currently a math and stats graduate from the University of Warwick with an incoming master's at the University of Cambridge. His background includes working as a quant researcher on the buy side and an equity derivatives intern on the sell side. Enough of me, let me pass on to Raul.
Thank you, Esther. I'm glad to have everyone today. We're going to talk about making a blockchain from scratch. So without further ado, let's begin. In terms of content, we're going to be covering some basics about hashing for people that don't have the background, and we're going to give a password cracking attack example, and then talk just about blockchain for the rest of the talk. To end with the Q&A section. So a bit about hashing. So is there a fast way to hide objects in a huge space? Imagine you have a huge storehouse and you have a very efficient robotic arm. When a package comes in, the robot takes a look and has a fixed place for it somewhere in the back, right? So the robot's execution time, it takes the package, it has a look, it puts it in the back. It doesn't care about how big the storehouse is, so that's the trick. But it cares about how big the package is. But we're not going to be concerned with that. It doesn't matter for the blockchain purpose. Two identical packages will be put in the same place if you make two requests for the robot. A slightly different package will be put in a totally different place. Okay, and you can have any type of data, and the storehouse distribution is uniform. So just no place is more likely to be an address, a final address, than another. So what's the catch, right? So reverse engineering is not possible here. Why? Because asking what objects sit at a specific address is just not feasible. You cannot find out. The robot will not be able to tell you that. All it does, it gives you the address, and you don't really know. You know how the robot works, but you cannot make the inference backwards. We can have collisions. Two different packages can be put at the same address, but if the warehouse is big enough, we really don't care about that. So let me just give you an example. Actually, taking the modulo a number, so the reminder when you just do an integer division, actually provides you with a hashing function. So just take some package, which is an integer, and you put it through your modular function, and you get your address, right? This is where it is sitting in the warehouse. But this is a weak form of hashing. Why? Because okay, so if I get 25 as my output, as you can see in the Python code, what was X there? Like we can roughly say it was 25 plus a multiple of 1039, right? But a good hashing function, you will not be able to do that. But no worries, Bitcoin and blockchain in general will not use such a simple hashing function. We'll use the SHA-256. And let's look at a simple example of how it works. So we are just trying to encrypt here the string WDSS 12 August 2020, and we get some output. We do it again, we get the same output. So same package, same output, same address. What if we slightly change it to 13 August? We get a completely different output. And this is important because you cannot tweak things around to make it work for you. You cannot be smart about cracking passwords, as you'll see. You just have to brute force it. So actually, I was just about to say, in terms of output space, the size of the warehouse, it's very big. It's about, you can compare the output space with the number of atoms in the universe. So that's big enough. So in the description, you will have a true blue, one brown video on the SHA-256 hashing function, and it's a great resource. You can watch it if you want to know more about it. Back to our password cracking example. So let's assume a hacker can see. Let's assume a hacker can see your first 3 letters of your passwords, and here's at most 6 other keystrokes. So it has some information about you. Let's also suppose it can crack the specific website you were using and get the hash out of there. Now, this is kind of silly. Websites will not store passwords and will not store the hashes of the passwords either. Just a bad website would do that, but let's just assume this for the time being. So the hacker goes home and runs a brute force. It knows the prefix of your password. It just has to guess the suffix, and it, all there is to it, it has to match your hash, right? Now the thing is, different packages of data would have had the same hash, right? The same address in the storehouse. So you could have collisions, but the probability is so small that if the hacker finds a suffix to match your password hash, it's most likely going to be your actual password. So don't worry too much about the specific code. Here is just a function that runs over all the possible suffixes, right? So it's just like an iterator for people who know what that is. And just a quick example of how the iterator would work: if you have DAZZ, you would just turn that into DBAA. So you kind of see the pattern, right? But if you had ZZZ, you would turn it into AAA. So not a big deal. We have the prefix, an empty suffix, and the target hash. And we want to see how much does it take us to do this password cracking thing, right? So until we have the hash that we're looking for, we're going to be iterating over all those possible combinations, and we're going to stop when we have it. So I ran this myself on an Intel i7, and I got about 10 minutes, right? So it's not trivial. It's not like you're loading a web page. It actually takes some time, and this password cracking will help you better understand the computational work that's going into blockchain, right? So you'll see in a second. So about blockchain, it was created by an individual, Satoshi Nakamoto, is actually anonymous. The idea was to avoid centralized systems. So you are all familiarized with centralized databases, storing information. Someone is managing that database, but with blockchain, you would have a network of people storing information on their end and having a protocol of communication to agree on what's good. And you will see that because we're talking about a chain, and various people will store their own version of the chain. When they're communicating, they will always agree on the longest one, because there will be there is this concept of work, of you have to deliver proof of work, which is related to our password cracking. So you will see in a second that. A lot of questions, right? Security, responsibility, consensus, implementation, who does that, how it is done. We're trying to answer some of them. And I will in no way try to re-implement Bitcoin or any other cryptocurrency. This is my own version of it. It has some limitations. I'm just running it on my computer. So my computer is definitely not a network, right? So before we go any further, just forget anything you are used to. There is no single place the data will be stored. It's a lot of places. And you were used to that account balance. You can see your account balance. Forget about that. Wallets will display it for you, but behind the scenes, any blockchain, Bitcoin in particular, will just store the transactions. Someone will have to compile those. Important to know the player in the network. So you can have the light clients, people that are not interested in the whole network. They just want to mind their business, do their transactions, not be bothered really. And you have the full nodes, which will actually download the entire chain and will set up communication to achieve consensus, always look for the longest chain, and so on. So the full nodes are just like, imagine they are guarding the blockchain. So this is what I want you to imagine. You have a network and it's not fully connected, right? There are degrees of separation into it. So if you're a full node, you might be communicating with some other full nodes, but you'll never reach everyone from one jump. But actually, if you've heard of the 6 degrees of separations, it applies. So you can reach anyone in like 6 steps. Okay, so let's look into some code. So for this section, I will not be focusing on details. I want you to understand the main structure of blockchain and how various, methods, pieces of functionality interact with each other to secure the blockchain, to manage transactions, and so on. Okay, so let's look at a block's content. So if we have a chain, you can imagine you would stack those chains on top of each other. You would stack the blocks in a chain. So you could think of depth or height or an index. I called it depth, right? So the block will have a depth. It will have transactions. This is what we're after. And it will have a timestamp. So at the time of the creation, it will be given a timestamp. But the previous hash and the nonce, so this is the subtlety here, right? So it's a chain linked by this way of passing the block's hash, which is the information in the block encoded. You would pass that to the next block, okay? And you will pass the hash of that block as the previous hash of the next block, and so on. So you will always store in your block information about the previous block. So why does that matter? Because if you're 10 blocks deep and you want to change something at the base, you will have changed the information of your block. Therefore, you will have changed the hash of your block. Therefore, the previous hash of the next block. Therefore, the hash of the next block and the previous hash of the next block, and so on. So you can kind of see what's happening. You cannot change anything without the whole thing falling apart. So there's one more thing really to consider. If you cannot change anything without, like, what does stop you from doing so? Like, why can't you just broadcast information to anyone about your changes, and why can't you do that instantaneously? So here's the catch. To go from one block to the other, you have to do a process similar to the password cracking, right? So it takes you time actually to discover some blocks. So if you were at block 0 trying to change it, you will affect block 10, and no one will trust you anymore. You will have to do all the work on your own, all the work that everyone else in the world has done to be able to recover, to be able to essentially broadcast the information as you want it. So let's look a bit closer into the structure of the blockchain. So we would have outstanding transactions that are being pushed by clients. We would store the main chain, and optionally, I mean, Bitcoin has a rule about this. We could store chains that have been validated but are no longer the longest chain. So just imagine like dead ends of rivers. Okay. Okay. So first of all, we create a genesis block. We start from something, and here the most important pieces of functionalities are: you can add blocks, right? I have two functions, adding blocks to the longest chain and adding blocks somewhere else, anywhere really, because you can do that, but it'll be harder for you to push that information out there. You have to do internal consensus in that if you're trying to actually push an attack from behind the blockchain, it's just a matter of telling yourself when you've actually you've bested your longest chain. It's not that important. Really, what's the bread and butter is the proof of work. So that will be the equivalent of the password cracking. So you will have the content of the block, and that will be the prefix in your password cracking example, and the suffix will be a dummy variable called nonce, which you can see here on the last slide. So that's just a degree of freedom which you have to brute force in order to find a hash which satisfies a condition. That condition is find me a hash with a number of starting zeros. And the number of starting zeros is the difficulty of the blockchain. So in order to move on, you have to do this mining process. So maybe a lot of you are familiarized with the term mining. You have to mine from one block to the other by doing this proof of work and essentially solving this computational problem. Okay, you can add new transactions, remove transactions that have been dealt with, and you also have to check whether a proof is valid or not. If you add a block, if someone wants you to add a block and gives you wrong proof, you don't want to add that, right? Okay, so with this rough structure, let's look a bit at the network components. We have full nodes, we have clients, and what can they do? Well, clients can only send transactions, okay? At least in my case, that's the only feature I want them to have. Full nodes will register on the network, will be able to download the entire blockchain, will do the external consensus, will check for all the other, not necessarily all the other, but check for other full nodes to see what they have as their consensus chain, as their longest chain, and match that with what we have internally. So we know we're keeping the information up to date, okay? And this longest mine method is essentially a method that enables the full node to work only at the longest chain. So, I mean, there are other possibilities, but I implemented my full node so that it only works at the longest chain. So it will have to do, I'm just reading quickly here. So it will have to check for outstanding transactions. It will have to establish external consensus. It will have to do the proof of work. I'm doing it in sprints, so in various pieces. I'm doing actually some sprints of proof of work, and then I'm checking the network. I'm doing proof of work. I'm checking the network to see if anything changed, right? Because if something changed and I'm working on the old version, I'm not making any progress really. I mean, unless I plan some attack. So that's roughly it. So you have the nodes downloading the blockchain, keeping it, verifying it. They are the guards of the blockchain, okay? And you have clients just sending transactions, okay? We're not actually going to go into details because I think the structure is what matters. So I'm going to explain how can you attack such a data structure, call it. Okay, so we're relying on computational power. Imagine that having computational power or having more computational power is like having more votes, buying votes, if you wish. That's not ethical though, but here you can acquire as much computational power as you're able to. So what happens is someone just has a monopoly on that. what happens to our blockchain? Essentially, they are able to mine faster than anyone else. They are able to discover and broadcast whatever blocks they want, and the network cannot do anything about it, because this is what democracy, I mean, proof of work is kind of a spoiled way of setting democracy. There's proof of stake as well, which kind of addresses that. But proof of work was the first one, is the one working with in Bitcoin right now. Okay, so what happens then? By the way, this is unlikely to happen in like Bitcoin, but you know, not cryptocurrencies that are not as mature have suffered of that. An example is the Ethereum Classic. So just imagine you have this chain, and at some point A stands to B, 10 coin. A stands for attacker. Okay, just look at the time setting. Okay, and A stands to B, 10 coin. But what really happens? B will want to wait for the transaction to be confirmed by other two blocks on the top of the block where that transaction has occurred. But in the privately, A has started to mine their own blocks, which are the red blocks depicted here, without the A to B transactions, but rather A sending those coins to themselves in order to double spend. This is called double spending. So at time 4, when the goods were sent, you can see that the attacker is one step behind, but it will now run at full power to catch up. And this is what happens. It will catch up, and the whole network will just move to the other branch. The consensus chain is now the time 0, time 1, and the red subchain. Okay, so there are two options here. Either the network is good and has ways of checking this, and full nodes should be able to spot this if it's not very well implemented, or it will just, or everyone will just take it for granted and kind of switch to the red chain. So it really depends on the network implementation if they're able to catch it. Ethereum Classic, for instance, was able to catch it, and I think the person got banned or something. So yeah. So the kind of what I want you to understand, that more recent blocks are more dangerous, and blocks in the past are less dangerous, are better established. Okay. So before we delve into the Q&A, I'm actually going to show you a little application. So the code that I've been showing you, it actually has a purpose, right? So all those full nodes, I can instantiate 4 full nodes, for instance, put them on different threads, run them, actually have a client send some transactions in. So I have some work to do as a full node, and let the threads run. So they are mining the transactions. So let's see what happens. Let's see if the chains manage to get along, right? Because we don't know if the chains will communicate properly. So my results have just loaded. We have 4 nodes, and let's look how they agree. Like this is the first column is the chain for the first node. The second column would be the chain for the second node, and so on. So at depth 0, everyone has the genesis. Depth 1, you can see by the hash, right? So you see the hash. Everyone has the same hash. They all agree with each other. As you go down, because I scheduled them to stop working, and when they stopped working, they had like a delay where they didn't check the network anymore. So you can see, for instance, depth 5 on node 4 has lost the consensus. The consensus here seems to be a hash with 00009. You see, we're using a difficulty of 4. So node 4 has just stopped mining, is not paying attention to the network. And the other ones are doing fine. Node 0 has stopped working, or node 1. Okay, and it seems like the last consensus was here between the two nodes, and just the third node went a bit longer. So these are all the outstanding transactions that those blocks have left over, because I scheduled them to stop. They haven't been able to process all the transactions, so there are still some transactions left over. If they were to start mining again, they would be able to, continue from where they've left and mine those transactions. Okay, so that would pretty much be it on my end. We're now in the Q&A section, so if you have any questions, feel free to leave them in the question sections, and I'll check for them. So yeah, by the way, feel free if you have any questions afterwards. If you're watching this after the stream has ended, you can find me on LinkedIn. You can ask me any questions about it. We can chat if you want to find out more. We can share information. Also, I put all the code that I've just ran. I put it on GitHub, and you can see the link here and in the description. So that will be it. So thank you very much for tuning in. I hope that was a nice presentation. So I'm now passing it on to Yasser. So thank you very much.
Thanks, Raul, for this talk. It was great having you here, and I learned a lot myself. I personally loved hearing about the idea of proof of work using the password cracking example and the integrity of blockchain in regards to cyber attacks. If you want to hear more talks and keep up to date with the society, please subscribe and follow us on our socials. We have some exciting news. We've just created a WDSS community group on Facebook. The group will be used for internal opportunities, so things like internship and graduate opportunities, and research projects, some of which are paid. We also want it to be a place where you can discuss data science and its applications. Next Friday, we also have a quiz night. This will contain some general trivia, so it's accessible for everyone, and will be hosted on Zoom. So have a look on our Facebook for the event. Thank you for watching, and we'll see you next time.